1211 quiz, off we go. 1 is cohesive. 2 is called a latent heat of fusion. If you just have latent heat, I'll go half. If you just had fusion, I'll go half. I can't give you the full point for just saying latent heat, because number 3 is also latent heat, but it's the latent heat of vaporization. There might be synonym names in this book. Let me do a quick check. No, that's just what they seem like they're consistently going with. Question about top 3. 4 were caloric, 5 is kinetic. One second. Everybody's doing the, not everybody's doing the today quiz, right? There's only one. Did you trade it in?
Evan has.
Okay, we should be good. Okay, so 5 was kinetic, 6 is Ke plus Pe of particles, 7 concerns the object as a whole, 8 is internal Ke, goes from high to low, 9's average Ke of particles, total Ke of particles, mercury thermometer, absolute 0 Kelvin, which is negative 273 Celsius. When energy is converted to heat, energy is conserved. Count Rumford. Then we got into entropy. The second law was heat flows from hot to cold. Unavailability of energy, 4.18 joules. The amount of heat to raise 1 gram by 1 degree Celsius. Delta Q equals MC delta T. And then yesterday's new question was the same as today's. That didn't change, so I pulled this paper for no real reason. That's the heat lost by 1 equals the heat gained by the other. Question about scoring anything? So where we are in terms of our cycle here, we're done reading for the chapter. 1211 was the end of the road. So what happens tomorrow is there'd be some homework due that's going from 22 to 29. Then we've got a nice long weekend with Monday off. Tuesday would be the book chapter review. There's questions 1 to 9, problems 1 to 13. Wednesday would be the review sheet that I gave you, the practice test for Wednesday. We would take the test on Thursday. The next quiz is going to be titled like 1211B, and I don't have a copy of that in my hand. It's probably in my practice test folder because it's probably the same as the practice test vocab. It says here that the quiz is 35. Does the vocab on the practice test go to 35? Yeah, so that's what that is. The next quiz is the practice test. So I would think, let's do that one tomorrow, and then we'll make a verdict tomorrow whether you want to do it again on Tuesday or whether doing once you've had your fill and you're good with that. But that would be the quiz tomorrow, is the vocab practice test. In terms of notes to tell you about on this paper, one important thing, whether it makes the quiz or doesn't, is temperature of things does not change while it's melting or boiling. That does not happen. Water can only melt when ice can only melt into water at what temperature? It's the melting point for ice.
Just above freezing?
No, it's a specific number. It's a magic number. We talked about another day. Ice can only melt at a specific temperature, which is 0 degrees. 0 degrees Celsius is the only only temperature where ice can melt. So if you've got ice that's negative 6 degrees, it will not melt until you have let it warm up a little bit to 0. And then once it's 0, it will melt. Water that is at 3, you can't freeze it. You can't freeze water that's 3 degrees until you cool it down to 0. All ice is created at 0. All ice is destroyed at 0. All conversions from ice to water are done at exactly 0 degrees. Things can't melt or freeze at any temperature with water other than zeros. Likewise, boiling. Water can only boil at 100. Steam can only condense at 100. That's it. You can't have steam that's 120 and have it condense. The only way steam at 120 will condense is if first you let it cool down. Water that's 70 can't boil until you first heat it up.
So like, if you look on the weather app and it says like the temperature and it says like the real feel, an object still couldn't freeze if it's like real feels like.
No, the real feel doesn't do it for you.
Okay.
Probably, you know, wind could maybe change the game. So if it's wind involved, I could see that maybe being a factor. But that real feel, I'm a little bit murky on what that real feel means. But there can be things like if there's pressure changes, it can change those melting and boiling points.
Okay.
There are things that can change them, but unless there's one of those external factors, not so much. But yeah, if you went, you go up in the mountains where the pressure is different, you go to the top of the Alps, water won't boil at 100, it would boil at like 80 because the pressure is, there's pressure differentials. And we'll get into that in future days. That's coming. Question about that theme, I don't know that that makes a quiz thing, but that's just an important like understanding of this. I have a little summary of number 2, so maybe jot down the summary of number 2 in case this matters on a quiz question or a chapter review question or something. But this is what I wrote for 2. If you have heat, heat does work. What that heat is doing work to do is forcing molecules apart. And whenever you're forcing molecules apart, you're increasing potential energy. That's what's going on here as we undergo these like changes of state. There's heat doing work. Work is forcing the molecules apart. The molecules getting forced apart is increasing potential energy. It's going to let the particles maybe start to move now that they're farther apart, but you're going to get things happen like melting and all that because there's heat doing work. The work is doing stuff to the molecules. The molecules are having energy changes. That's what's going on in this world. If that doesn't make total sense to you, you're never going to see a molecule, so you'll probably be okay. Question about what's the next quiz, question about what's going on. Well, let's do some math. Okay, so if you look with me at page 199, we're going to need some of these numbers on page 199. There's a new table for these latent heats. So what the homework math life is going to ask you to do is things like, there's 200 grams of water, let's say that it is at 100 degrees already. If we have 200 grams of water that's already at 100 degrees, and I want to know how many joules it's going to take to make that water boil, what you're going to have to do is just multiply a mass by a latent heat. I don't have an equation for this. The book doesn't have an equation for this. It's just the way it is. When you're changing states, you want to just take a mass times a latent heat. So for this, if I have 200 grams of water that I want to boil, I just need to take 200 times the right number. Can anybody on page 199 find me the correct number for boiling water? You've got a 50-50 shot, or maybe better than a 50-50 shot if you think about it a little bit. Anybody 199 willing to take a stab at what is the number for water boiling? Well, let's try this question. What would be potentially a number that might be in play? Because I said it's 50-50, that you might. Okay, 334 might be in play. Who else might be in play? 2,260. Why are those the two that are in play? They're both for water. Okay, so one of those is right, one of those is wrong. Anybody willing to take a stab at which one is the right number for boiling water? Correct. Why? Vaporize, yeah. Another word for steam could be vapor. Another word for gas is vapor. The vaporization numbers are when gases are involved. So if we're boiling, that's a gas involved. We want to use the 2260, that's a vaporization number. Fusion has to do with solids. So if I wanted to use the 334 with water, what would that be for? Freezing it. So if I ask you to freeze 200 grams of water, that's still, and I'd have to commit to that water is already at 0 degrees, because if the water's not at 0, it won't freeze. But if the water's at 0 and I want to freeze it, the joules on that would be the 200 mass times 334. Question about that? And let's all add on a level of complication. What if I start, well, I'll do a small twist, then I'll make it more complicated. If I asked you if you were going to melt 200 grams of ice, how many joules you'd get out of that? Anybody have a thought on what would happen if instead of freezing water, I asked you to melt ice? And instead of asking you about joules going in, I ask you about joules that would come out?
Would you go high?
No, that's a decent thought because we're opposites, but no. A thought on the joule count? It is the same. It would be the same number. So whether you're melting or freezing ice or water, we're going to use the 334. What's the opposite of boiling? Like melting is opposite of freezing. What's the opposite of boiling? It's a C word.
Condensing.
Yeah, condensing.
Condensing.
So if they're talking about boiling or condensing, water or steam, it doesn't matter. It would be the same number. Question about that flip of the coin? Long story short, anything that has to do with a solid, whether you're making a solid or unmaking a solid, that's the fusions. If you're making a gas or unmaking a gas, that's the vaporization. There's always got to be a liquid involved. Okay? I think later we'll talk about, on occasion you can go straight from gas to solid or solid to gas. Does anybody know those words? If you skip the liquid and you go straight from one to the other, it's a physical science word. You've had it because I know my son just studied this word like a week ago. Nobody remembers? Just have to wait and see. Teaser for future physics. But there's a word for if you skip the liquid and go straight from solid to gas or gas to solid. But through this chapter, we're going to go through the liquid phase. Questions at all? Okay, so here's a complication. Let's say I give you ice at 0, and I want you to make me steam that's at 100. So our ice is 0 already. The goal is steam that is 100. Would you have to do this math? Yes, because we have to melt that ice to make that happen. But we still need to do this math. Yes, because we still have to boil the thing to make that happen. But what are we missing? What's going to happen in the real world if your ice is 0 and you want to make steam that's 100, that's not a two-step plan. That's not as simple as we'll melt the ice and then boil the water. You'd have to heat the water up. So this now just became a 3-step plan. If I gave you ice that's 0, you'd have to melt it. Then you'd have to heat up the water. Then you'd have to boil that water that's hot water instead of cold water. Cold water can't boil. Water can only boil at 100. How do we do the math for heating up that water? That's not new today, that's old. ish. Well, subtracting is involved, but how do we do the joules it would take to heat stuff up? How do we do that math? Yeah, we're doing that MC delta T thing. So we would take a mass times, what's the specific heat for water? 4.18. And how much of a temperature change did we have undergone in this story? 100 degrees. We'd have to do this, take the three results and do what to them? Add them up. So it would be a three-step plan if we're trying to have ice that's 0, get it to be steam that's at 100. Question about that? Then let me add on a step 4. What if I want to make that steam be 130 degrees? That would add on another level. How would you do the math for making steam be 130 degrees instead of a minute ago we left it off being only 100 degrees? Yeah, we're doing one of those MC delta T things again. The mass is 200. What's steam's number? I always get it confused with ice until I get back in the flow of this. This is the first time I've seen this number this year, so I doubted myself. For steam, it is 2.02. What's the temperature change here that the steam alone did? 30. If I want a total answer, I'm going to have to do all 4 levels. I'm going to have to add them all up. There is no shortcut to do that. Each level is its own math. How can I make this one step meaner? And this is as mean as it could be. Well, start from where? Where could I start the process from to make this harder to even do? Make the ice colder. So let me renumber. If I told you a story where my ice is originally -10 degrees, we'd have to warm the ice from -10 degrees before we could even melt it. So if I said, hey, I've got super cold ice that's negative, I want you to make super hot steam that's over 130, you're going to have to go through 5 transitions. The ice can't melt until it's warmed up to 0, then melt it. Then change the temperature again to get the water up to 100. Then you can boil it. Then you have to change the temperature again. Anytime you're changing temperatures, it's the MC delta T. Anytime you're changing state, solid to liquid, liquid to gas, that kind of stuff, it's just mass times latent heat. So warming up the ice, it's still 200 grams. What's the number for ice changing temperature? Anybody? Ice from the table? 2.06. Temperature change is only 10. Because we're not worried about, we're not making this dramatic of a temperature change straight from here to here. You have to take these baby steps. From -10 to 0, do a change. From 0 to 100, do a change. From 100 to 130, do a change. And then when you hit the thresholds, the border lines between states, you have to do this mass times latent heat. Now you got 5 things. Add them up, that's as big as it gets. There is no 5-step plan in the homework. Pretty sure there is a 5-step plan in the chapter review. I'm positive there will be a 5-step plan on the test, where you'd have to go from one extreme to the other. And if I asked you to go from ice to steam, that takes energy to be absorbed. If I asked you to go from steam to ice, that would be energy being released, but the number would be the same. So it doesn't matter what order you do the steps in, really. It doesn't matter which direction we're taking the joules. Either energy's going in or energy's coming out, but it's the same. Question? question about that? If you don't get it, I'll repeat myself. If you get it, I don't want to sit here and just keep saying the same thing over and over. So let me make up a slightly smaller problem, and then we'll call it a day. Oh, pick a mass. How much mass you want?
Huh?
How much mass?
50.
50 grams. Pick ice, water, or steam.
Ice.
Ice. At, you want it, it's like a Mad Lib, it's like a physics Mad Lib. Do you want to be at 0 or colder? Colder. How cold do you want to be?
-2.
-2 degrees. We're going to turn that into water at 70 degrees. How many math steps is this going to take us to do this? 3. Just in English, what would be the first little thing that has to happen to this ice? Warm the ice. Is there an equation or no equation for temperature change time? Equation. What is it? MC delta T. In English, what's the next thing that would have to happen after the ice was warm enough to cooperate? Melt. Is there an equation for that or just math? Just math. Just multiply the right two numbers. Now we've got water. We melted it, we got water, but that water is cold water. Then what has to happen? Warm up the water. If we're warming up water, equation, no equation, equation, MC delta T. So with these particular numbers, how much is the mass? 50, so 50, 50, 50. When it's ice time, what's the ice warming up number? And I still doubt myself because it starts off 2.0 and then it's an even number and they're almost the same. It makes me mad, but eventually I'll get it figured out and won't peak every time. That's the 2.06. Temperature change is 2. Because we're only trying to get from -2 to 0. We're not even worried about 70. We're just worried about getting the ice warmed up a little bit. What was the melt freeze number? .260 or 334? 334. Since we're dealing with ice, ice is a solid, solid's the fusions. We're going to use the fusion number for anything involving ice. And I think they put ice in parentheses, didn't they? Yeah, so the one that they have ice in parentheses, that may help us out. They didn't put steam in parentheses, but if they put ice on the one, you know steam is on the other side. Warming up water, what's the number for water? 4.18. And how much is a water temperature change for this story based on our Mad Lib?
7.
7. You know what I mean by Mad Libs? Done this, some people get. It's like to say pick an adjective, pick the color, and like making sentences. It's always just like crazy at the end. But we punch each of these in individually, add them up, see what it is. So you have a joule count on all that. Homework's going to have some one-step plans. It'll have some two-step plans. I think it has maybe some three-step plans. I don't think it has five-step plans yet, but if it does, we'll survive it because we're going to do that sooner or later. But homework off of this is again from 22 to 29, then a chapter review, then a book, or then a worksheet review, and we go. Answers today, we can dig in and do some stuff here. 16 is a problem. Did anybody in 16 have an answer in the 40s?
45.
It is 45. Anybody for 18 have a slightly bigger number than 45? Yeah, mine rounded it to 60, but that seems like you went another digit, and that's fine, because on the test we like 3 digits anyway. 20 is a decimal number slightly less than 1. It's a little lower than that. It's a .80 kind of thing. Anybody on 20 get a .8 kind of thing? Yeah, the number from the table for aluminum is .903, but this aluminum is going to be not that number. I would speculate either their information didn't accurately reflect light, or potentially there's different kinds of aluminum. Like there's a thing called isotopes, that there's different types of certain elements and they do different things on you. But this should start with a .8 kind of thing. Does anybody need assistance with something 16 to 21? Okay, let's